At first glance, the idea of particles that pop in and out of existence sounds like science fiction. Particles that aren't really there, that exist for a fleeting moment and then vanish. How could such ghostly entities matter at all? And yet, these so called virtual particles are at the heart of modern physics. They help explain how forces work, how atoms behave, and why even the emptiest vacuum is never truly empty. But here's the strange part. If virtual particles are too short-lived to be seen or measured directly, how can they possibly have real, measurable effects? This puzzling idea is known as the virtual particle lifetime paradox. Let's take a step back. In quantum physics, the vacuum isn't just empty space. It's more like a restless ocean of energy, constantly bubbling with activity. Even in total darkness, even in the absence of all matter, the quantum fields that fill space are always fluctuating. From these fluctuations, virtual particles briefly appear, like tiny waves rising and falling in that invisible ocean. They don't last long. They can't be detected directly. But somehow, their presence changes the behavior of the universe in ways we can measure. How? Imagine you're at a quiet pond. Suddenly, even though you didn't see anything fall in, ripples begin to move across the surface. Something unseen has disturbed the water. Virtual particles are like those ripples. They're signs of invisible processes happening just beneath the surface of what we can observe. One of the best known examples is the Lamb shift, discovered in hydrogen atoms. Scientists found that one of the energy levels was slightly off from where it should be. At first, it made no sense, but then they realized the electron in the atom isn't orbiting quietly. It's being gently nudged by a sea of virtual photons, constantly flickering into existence and disappearing. The combined effect of these ghost particles actually shifts the energy of the atom, and that shift can be measured with great precision. Or take the Casimir effect, a strange force that appears when two metal plates are placed very close together in a vacuum. There's nothing between them, no air, no light, nothing. And yet they attract each other. Why? Because the space between the plates can't support as many virtual particle fluctuations as the space outside. This imbalance creates a subtle pressure, nudging the plates inward. It's like the vacuum itself is pushing them together. You might ask, but if virtual particles don't last long enough to be seen, aren't they just imaginary? That's the heart of the paradox. They are imaginary in the sense that they're part of the math we use to describe quantum processes. They're not particles flying around like tiny marbles, but their collective influence is real. Think of it like a crowd whispering in a room. You can't hear any one voice clearly, but together they create a hum that changes the entire atmosphere. Even the way forces work, like electromagnetism, relies on virtual particles. When two electrons repel each other, it's not because they see each other in the traditional sense. Instead, they're exchanging virtual photons, momentary particles that carry force from one to the other. It's as if they're throwing invisible baseballs back and forth, too fast and too small to catch, but enough to feel the impact. And the weirdness doesn't stop there. In the quantum world, not only do things happen that we can't see, but even things that don't actually happen can still influence the outcome. Virtual particles are a perfect example. They're possibilities that briefly become reality. And even though they vanish almost immediately, their fingerprints remain. So, how can something that doesn't really exist still shape what's real? Because in quantum physics, possibilities are powerful. Every possible path a particle might take contributes to what actually happens. The virtual particles are like whispers of alternate outcomes, flickering possibilities that, even if they're never fully realized, still change the story. Could we ever find a way to see them directly? Maybe not in the traditional sense, but through the shifts, forces, and interactions they produce, we already know they're there. They may live only for a fleeting moment, but they are part of the engine that runs the universe. And perhaps that's the most mind-bending part of all, that the fabric of reality is constantly shaped by things that don't seem real at all. The virtual becomes vital, the invisible becomes essential. And the paradox? It's a reminder that not everything that matters has to last, or even be seen to leave a mark on the universe. Virtual particles are transient fluctuations emerging from the quantum vacuum, appearing and vanishing in accordance with the Heisenberg uncertainty principle. They exist only briefly, borrowing energy for a time short enough to comply with quantum rules and are not directly observable. Despite their fleeting lifetimes, they contribute to measurable physical effects by mediating forces between particles. Their existence is a cornerstone of quantum field theory, providing a mechanism for interactions that influence macroscopic phenomena. Example, the Casimir effect, where two uncharged metal plates attract each other due to the altered vacuum energy between them, is a direct consequence of virtual particle fluctuation analogy. It's like noticing a subtle pressure difference in a room caused by tiny, invisible gusts of wind that appear and vanish rapidly, yet collectively exert a measurable force. The paradox arises from the observation that virtual particles seem to exist for durations that, on the surface, challenge classical energy conservation principles. According to the uncertainty principle, these particles borrow energy from the vacuum for an extremely short time, during which they contribute to physical processes before annihilating. Despite this ephemeral existence, the cumulative impact of countless virtual particles produces observable effects, such as shifts in atomic energy levels. The paradox thus lies in reconciling their transient nature with their enduring, measurable influence. Example, in quantum electrodynamics, QED, virtual particles in loop diagrams contribute to corrections that match experimental values with incredible precision. Analogy. It's like a series of tiny momentary whispers that, though individually fleeting, combine to produce a clear, discernible message. The Heisenberg uncertainty principle allows for temporary violations of energy conservation, stating that the product of the uncertainties in energy and time has a lower bound. Virtual particles exploit this principle by existing only for a time short enough that the uncertainty relation is satisfied. Their lifetimes are inversely proportional to the energy they borrow, making higher energy fluctuations even more fleeting. This mechanism explains how they can appear and vanish without violating the overall conservation laws of physics. Example, a virtual electron-positron pair may exist for an extremely short time, its lifetime dictated by the energy associated with its creation, yet its influence is observable through its contribution to vacuum polarization. Analogy, it's like taking a tiny brief loan that must be repaid almost immediately, short enough that the transaction doesn't upset the overall balance, but with measurable impact. Virtual particles contribute to measurable effects, such as vacuum polarization, where they temporarily modify the effective charge and electromagnetic fields around particles. These fluctuations can lead to observable energy shifts, such as the Lamb shift in hydrogen atoms, where energy levels are slightly altered due to the presence of virtual particles. Even though these particles are not directly observed, their aggregate effects can be precisely measured and have been experimentally verified. Such phenomena underscore the tangible impact of processes that occur at the quantum level. Example, the Lamb shift, an energy difference between two quantum states in the hydrogen atom, arises because of interactions with virtual particles that perturb the electron's electromagnetic environment. Analogy, it's like small ripples in a pond that subtly change the water's surface level, even though each individual ripple is too brief to notice on its own. In quantum field theory, virtual particles appear as internal lines in Feynman diagrams, representing the intermediate states in particle interactions. These virtual loops contribute to quantum corrections that adjust the properties of particles, such as mass and charge, ensuring that theoretical predictions align with experimental observations. Each loop, though composed of transient particles, collectively produces significant cumulative effects over many interactions. This framework is crucial for understanding and calculating processes in particle physics. Example, calculations of the electron's anomalous magnetic moment involve summing over virtual particle loop contributions, resulting in predictions that match experimental values to an extraordinary degree. Analogy, it's like piecing together hundreds of tiny puzzle fragments that, while each is momentary and small, combine to form a complete and accurate picture. The effects of virtual particles emerge from the interference between the probability amplitudes of different quantum states, leading to constructive or destructive interference. While each virtual particle is ephemeral, their combined interference can significantly modify observable quantities like force strengths and energy levels. This collective behavior demonstrates that even transient quantum events can have a lasting impact on macroscopic property. The overall effect of these fluctuations is integrated into the behavior of quantum fields, contributing to phenomena that are measurable in experiments. Example, vacuum polarization, where the collective interference of virtual electron-positron pairs alters the effective charge distribution around a particle, is a classic example of these cumulative effects. Analogy, it's like countless tiny ripples on a lake interfering to produce a significant overall wave pattern that affects the entire surface. Renormalization is the process by which infinities arising from the summation of virtual particle contributions are systematically removed or absorbed into redefined physical constants. This mathematical technique allows quantum field theories to yield finite, precise predictions despite the seemingly infinite number of transient fluctuations in the vacuum. Through renormalization, observable quantities such as particle masses and coupling constants are adjusted to account for the effects of virtual particles. This process ensures that the theory remains predictive and consistent with experimental data. Example, in QED, the divergent contributions from virtual particle loops are renormalized to yield the observed electron mass and charge, resulting in a theory that accurately predicts phenomena like the electron's magnetic moment. Analogy, it's like carefully balancing an intricate budget by absorbing small, unpredictable expenses into overall cost estimates, ensuring the final account remains accurate and manageable. The measurable effects of virtual particles have been confirmed through high-precision experiments such as those measuring the Casimir force, the Lamb shift, and the anomalous magnetic moment of the electron. These experimental verifications provide robust support for the theoretical framework of quantum field theory. Moreover, understanding virtual particles has practical implications in nanotechnology and material science, where vacuum fluctuations can influence forces at the nanoscale. As experimental techniques advance, we continue to refine our understanding of these subtle quantum effects and their applications. Example, micro-electromechanical systems, MEMS, have been used to measure the Casimir effect with high accuracy, directly validating predictions based on virtual particle fluctuations. Analogy, it's like using an ultra-sensitive scale to detect the faint push of a gentle breeze, confirming that even imperceptible forces can have measurable consequences when properly observed. Future research on virtual particle dynamics promises to deepen our understanding of the quantum vacuum and may reveal new physics beyond the standard model. Advances in experimental methods such as ultra-high-resolution spectroscopy and nanoscale force measurements will further clarify the role of virtual particles in fundamental interactions. These studies also raise philosophical questions about the nature of nothingness and the role of fluctuations in shaping reality. Ultimately, while virtual particles remain fleeting, their collective impact is integral to the structure of the universe, challenging our perceptions of existence and emptiness. Example, cutting-edge research is exploring whether harnessing virtual particle fluctuations could lead to new energy technologies or novel methods of information transfer, pushing the boundaries of both physics and engineering. Analogy, it's like discovering that the seemingly empty space in a quiet room is teeming with hidden currents and subtle forces. Forces that, though invisible, shape the entire environment in profound ways.